Some time ago, I invented a new type of solitaire. It has very simple rules. Take a randomly shuffled deck of cards and draw cards from the top. Every black card gives you points, or dollars, equal to its face value. Every red card puts you in a red by the same amount.
Aces are worth 1, jacks are worth 11, queens are worth 12, and kings 13.
You can stop play at any time and take your winnings. Since the black cards and the red cards are equal in value, if you play to the end, going through the entire deck, you will always break even. -4, -13, -10, 3, and I'm going to stop right there and take my $3. Now, suppose you were to pay to play this game. How much would you be willing to pay? If you do it for free, you know that you'll break even, and you'll probably come out ahead at some point. So let's start by paying $1 to the dealer, start pulling out cards. The rule this time is as soon as I come out ahead by any amount, I'm going to stop playing. Oh, look, won $4. Minus the $1 I paid to play, I just won $3. $1 seems like a good bet. Since $1 worked out so well, this time I'm giving the dealer $5. Start flipping cards. -5, -18, -21, -18, -14, -15, 5, or -5, -13, -2, ooh, -13, -15, -21, -8. Oh, look! -8 plus 12 gives me 4. I won 4, but I paid $5 to get in. So, let's keep pulling. Look, that's 6. I paid 5 to get in. I won a total of $1.
To make this process a little bit easier, and to make it a little bit shorter, I said to go all the way through the deck 3 times and make charts of what I saw. So we'll see 3 random walks of the entire deck. Our first chart is about what you would expect. Goes down to -29, then goes gradually up to 26, and it kind of hovers around 0, up and down, off and on, until the end of the run. Looks like a pretty expected random walk. Our second chart does something that I didn't expect. The lowest it goes is to -8, and that's the only point in the entire run that it's negative. It mostly goes up and up until it hits 64, then it goes back down to 0. So this shows for a random walk, you can still have it all stay positive. Our third chart does pretty much the same thing as chart number 2, only the opposite. Goes down all the way to -56, hits that point twice, then climbs up to 30 before going down to 0. Spends most of its time in the negative zone. Intuitions about random events aren't always right. Since we start at 0 and have an even chance of going up or down, our intuition might tell us that we should stay pretty close to 0. But in reality, random walks like this have a lot of clumping, and it can go in one direction for quite a while. I don't know how to calculate the expected value of the highest random walk. There are, after all, 52 factorial combinations of playing cards, and I can't find an intuitive answer to just how much of a positive random walk to expect. If anyone is interested, feel free to share your guesses or computations.